Hi guys, welcome to HSC Chemistry and the final in the little series of production of materials topic. This is the start of radioactivity and it's the last of the 5 sections that we need to look at in this topic of production of materials. So in the first one of the final series we're going to look at nuclear stability and what it is that makes some isotopes unstable. So the first man we had to deal with is Henri Becquerel, who won the Nobel Prize in 1903, and whether or not you actually care, he was also voted the sexiest man alive in 1906. I guess that was the look back then. Becquerel was the one who discovered that a piece of photographic paper which was in contact, or at least in close proximity to some mineral containing uranium, actually created a, hang on, let's see if I can get a decent color going on here, that's better, containing uranium. And what happened was that the photographic paper behaved like it had been exposed, it darkened. So this made Becquerel think, well, maybe there's something interesting going on here. His discovery of radioactivity and the particles that were being released by the uranium and interfering with the photographic paper was something that contributed to his winning of the 1903 Nobel Prize for Chemistry. Pretty impressive start in the story of radioactivity. And here, the little dark patches that were created as a consequence of that exposure. Probably the most famous person, or the one that we perhaps associate more readily with radioactivity, is Marie Curie. She worked with her husband Pierre to find and isolate the elements polonium and radium, and they shared the 1903 Nobel Prize with Becquerel. Of course, we knew so little about radioactivity back then that the work that the Curies did in particular was so dangerous that it significantly affected their health and shortened their lifespan. We know the links now between radiation exposure and particularly cancers such as leukemia, and that was the one that we believe is claimed Marie Curie. 1934, so not a very long life for someone who was so significant in contributing to our understanding of a particular area of science and chemistry in the area of radioactivity. So I guess the first thing to do is to just quickly revise the structure of the atom, which is probably a useful thing. The electrons are the components that move around the nucleus of the atom, and they have almost no mass, so we don't really consider them particularly in this story. The protons are in the nucleus. They have a positive charge and they have a mass that's equivalent to that of a neutron. And of course the neutrons are in there as well, and they have the same mass as a proton. So this section on radioactivity or nuclear chemistry is really about the nucleus of the atom. What's in there, what's going on in there, why some atoms are more stable than others. So I guess the thing is that the key points are firstly that as far as mass is concerned, it's the proton and the neutron that are important. And as we might see later on when we start looking at the different types of radiation, the charge is also going to be important. And that's going to affect certain things like the ionizing ability of different types of particles. So when we look at any of these atoms or any of the elements in the periodic table, what we tend to notice is that we have a mass number which represents the number of protons plus the number of neutrons in the nucleus, and we have a symbol, and we have an atomic number, and the atomic number represents the number of protons. So therefore we can very easily get to the number of neutrons by subtracting the atomic mass from the mass number. So mass number minus the atomic mass is going to equal the number of neutrons. And this is going to be important as we start our assessment of stability, nuclear stability. So what are isotopes then? Well, again, this shouldn't be new stuff, so let's just quickly review it. An isotope is an atom with a different number of neutrons to the probably the most common form. So the most common form of oxygen is oxygen 16. So we call it oxygen 16. 16 because the 8 is the definer that this is oxygen. If the atomic number were not 8, it wouldn't be oxygen. 8 is the number of protons, and the number of protons actually defines the element. So that won't change for a particular element, and if it does, it's a different element. But the mass number can change, and the mass number can change based on the number of neutrons in the nucleus. So here is oxygen 17. In the standard case for oxygen 16, if there are 8 protons, then we must have 16 minus 8, which is 8 neutrons. For oxygen 17, of course, we now have 17 minus 8, which is 9 neutrons. So we've changed the number of neutrons. And of course, we can keep going for different isotopes. This one would be oxygen 18, and it will have 10 neutrons by the same calculation that we did before. That looks like iron, but believe me, it's 10 neutrons. So each of the isotopes has 8 protons, because if it didn't, it wouldn't be oxygen anymore. The number that's changing, the number that's important here, is the mass number. And the mass number is showing us that in each of these cases there is an additional neutron than there was in the most common or stable form of oxygen. The difference in the mass numbers, as I mentioned before, is just around those numbers of neutrons. The thing with isotopes is that they don't all occur equally. So, for example, when we look at carbon, carbon-12 is the most common isotope of carbon. In fact, almost 99% of carbon is carbon-12. Only a very small portion of carbon is any of the other isotopes. So carbon-13, which would have 7 neutrons, and carbon-14, which would have 8 neutrons. Incidentally, these different proportions are what enable us to calculate the values that you see on the periodic table for those atomic masses. So in order to calculate it, what the atomic mass would be, the mass would be calculated by looking at 0.9888 times 12 plus 0.0111 times 13 plus 0.001 times 14. And if we added all of those together, we would get something that was around about the area of 12.01. And that's what we would expect to get, given that's the value on the periodic table. So we need to look at how we represent each of these. In the past, if we've had elements involved in chemical reactions, we haven't had to worry about the mass number or the atomic number. We've just looked at the symbol. Now, of course, we know that the mass number can change, so this number here can change. So in order for us to understand what type of isotope we have, we need to actually represent our elements for nuclear reactions, not for every reaction, but for nuclear reactions, with the superscript, the 4 in this case, and the subscript, the 2 in this case. So this element over here is titanium. It would be titanium 48. Its mass number is 48. The 22 obviously indicates that there are 22 protons, and that corresponds to titanium. Now, for some elements, all of their isotopes are radioactive. So things like uranium doesn't come in a stable form. All of these are radioactive. So if you see uranium, you know that it's going to be unstable. For other elements, however, only some of their isotopes are radioactive. So there is a stable form of lead and an unstable form. There's the most stable form of carbon. We looked before at that. That's carbon-12. Carbon-14 is an unstable form. And titanium-44 is also an unstable form. Any of the isotopes that are radioactive or that emit radiation are known as radioisotopes. So that radio just comes in front of the isotope to indicate that it's unstable. So the important question in this section is, how do we know? How do we know which isotopes are going to be radioisotopes? Well, the radioisotope will be unstable if its atomic number is greater than 83. So that's the first test. If the atomic number is greater than 83, then it's unstable. Doesn't matter what it is. If it's that big, it's going to be unstable. But the second test for instability is the ratio of neutrons to protons. Okay? This is one of the key things that you're going to be looking for in order to determine whether or not a nucleus is stable or unstable. Now there is a little range here, a little zone, which we call the zone of stability. That zone of stability corresponds to a ratio of around about 1:1 neutrons to protons when the atomic number is less than 20. And again, hopefully you're starting to realize why in the junior school everything goes up to 20 and then we stop talking about it. But when it becomes larger than 20, then we have this 1.5:1 ratio, and that doesn't just shift with element number 21, it gradually increases. So because of that, we need to have a look at how that manifests itself. And here is what is called the zone of stability. So you can see there is a range here. The gray is the zone or the band of stability. So that's where the elements are stable nuclei, but the blue areas are where we have the unstable nuclei, or the radioisotopes. So you can see here just a plot of the number of protons to the number of neutrons, and you can see up to about 20, we've got a pretty much 1:1 ratio, but that is increasing in favor of the number of neutrons as we go further up. As the proton numbers increase, the number of neutrons needed to ensure the isotope is stable also increases, and any isotope outside the zone of stability will be radioactive. So let's see if we can put this into practice. Which of these sets contains only stable nuclei? Well, I guess what we're looking for when we see questions like this is we're looking for instability. The first thing we hopefully remember is that uranium is always unstable. So we're going to knock that one out to begin with. So we have 3 sets left. So obviously A can't be the correct answer. 3 sets left. Now we've got 2 choices here with hydrogen. There's a hydrogen here with a mass of 2 and a hydrogen here with a mass of 1. Now you would be aware that the most common form of hydrogen, the most stable form of hydrogen, is hydrogen 1. So this is a stable form, and this is an unstable form. So that's no good. So then we'll move on to, say, carbon. Here's one here, carbon 12. Now we know again that carbon 12 is the stable form of carbon, but here's another one here, carbon 14. The carbon 14 is an unstable form of carbon. So this one here is also going to be an unstable isotope, and so we can knock that one out. As we continue to go through this, we find that there's going to be elements that are going to move away from what we expect to be their standard number. So again, oxygen is less than 20, so we expect the ratio of neutrons to protons to be roughly 1:1 for those less than 20. So you can see oxygen here has a ratio of 1:1, 8 and 16 means 8:8. But this one over here is 8:10. So this is, again, not a stable ratio for the number of neutrons to protons. So this one, again, is not a good one. This one fits the 1:1 ratio. This one fits the 1:1 ratio. And for potassium, we're very close to the 1:1 ratio. It's just slightly larger, but it's the most stable form. And because we've eliminated all the other options, the correct answer must be B. Thanks for watching.